From this lecture, we are going to start a new series on single phase induction motor. In this series, we will try to cover up most of the topics of this single phase induction motor. Now, many of the students has the questions in their mind that why the single phase induction motor is so important or why we are studying it. The simple answer is, in our distribution section, mostly in our household runs in single phase supply. In this section, if we consider our household section, this is a ceiling fan, and what actually the motor inside the ceiling fan is? It is a single phase induction motor. If you consider about your water pumps that used to supply water in 1 or 2 storied building, then that water pumps is also a single phase induction motor. Clear? So whenever we are using a single phase induction motor, mostly in our domestic or household purposes, then this single phase induction motor has got a very significant role. Whether a 3-phase induction motor, mostly used in the industrial or large commercial purposes. Now, when we start to deal with the operating principle of a single phase induction motor, I found that most of the students struggles in understanding its basic principle, and the problem starts from the very question is whether this motor is self-starting or not. Now, I can assure you, if you mindfully observe this lecture, then after watching this lecture, you will have a proper knowledge on these working principles and the allied things in single phase induction motor. Now your question will be, why? To understand that, let us deal with this schematic diagram of a single phase induction motor. See, this is the rotor, and this RM and XM combination is the stator winding. Whenever this stator winding is connected with a single phase supply, then a pulsating magnetic field is created. Now your question will be, what is this pulsating magnetic field? See, this is a pulsating magnetic field. Now, what is of its character? It always changing its value. It's starting from a 0 value, then after some time it goes to the maximum value. This is the max value. Then again it is going to a 0 value, then again going to the negative max value, and again 0 value. So this kind of pulsating magnetic field is incapable of rotating the rotor. So your question will be, then what type of magnetic field is capable of rotating the rotor? It is the rotating magnetic field. Now, where do we find this kind of rotating magnetic field? When we studied the 3-phase induction motor, then this rotating magnetic field is created between the air gap between stator and rotor. That's why the 3-phase induction motor is self-starting. Clear? Now your question will be, then how could I rotate a single phase induction motor? See, whenever you are providing a single phase supply to the stator winding, then this pulsating magnetic field, by using this, you can rotate the single phase induction motor, but this process is not actually adapted because it requires a mechanical external force, and the main disadvantage of using this mechanical external force to rotate the motor is if the rotor is or the motor is at inaccessible position, then you cannot use this force to rotate the motor, or if the rotor is of heavy weight, then also this kind of external force starting is not possible. Then what is the solution? The simple solution is we use an auxiliary winding in order to starting the induction motor. This is a very important concept. Now your question will be, where will we connect this auxiliary winding? The simple answer is in parallel to the main winding. Now where is the main winding? This is the main winding. That's why the subscript has been given here, Rm and Xm. Okay, so if we try to create an auxiliary winding like this, here the resistance and the inductance are connected in series with each other but in parallel with the main winding. So we can say this combination as the auxiliary winding of the motor. Now you can ask that what is the difference between the main winding and auxiliary winding, and specifically how it is participating in rotation of the rotor. Now see, the main winding has low resistance and high inductance, and the auxiliary winding has high resistance and low inductance. Now your question will be why? Because whenever we are giving the supply stator winding, then suppose if a current is coming from the supply, that is I, then the main winding current may be Im and the auxiliary winding current may be Ia. Okay, so according to KCL, I is equal to Ia and Im. Now whenever I have increased the inductance of the main winding, then automatically the Im will be a lagging current, whereas Ia will lead compared to this Im. Now if we look into the phasor diagram, then as I have said, the Im will lag behind this Ia. And what angle? Suppose the angle is alpha, that is alpha is the angle between Im and Ia. So the generated torque, suppose tau, which will rotate the rotor, is equal to K Im Ia sine alpha. So the phase difference created between this Im and Ia, their multiplication is creating the torque which is actually rotating the single phase induction motor. Now for your information, this particular phase difference alpha is generally in the range of 25 degree to 30 degree. So in this way we can start a single phase induction motor, and when the motor has achieved almost 75 to 80% of its synchronous speed, then if you disconnect this auxiliary winding, then still the rotor can rotate. As I have said in the beginning of the operation that in any mechanical way, if you start or rotate the rotor will move or start to rotate. That is similar case in this case also. Here if you disconnect it, that means the auxiliary winding at 75 to 80% of its synchronous speed, then when the rotor has attained this speed, then the rotor will still rotate. That is, it further, it doesn't require the auxiliary winding or the phase difference current flow to sustain the rotation of the rotor. So I think you have understood this entire operation clearly. For any doubt, you can put your doubts at the comment section below. Thank you.